Hello everybody and welcome to my Linux Security Summit talk about patch attestation. My name is Konstantin Rabitsov. I am in charge of kernel.org infrastructure at the Linux Foundation. I've never done anything like this before. I'm not a professional recorder, so I hope it works out. There probably will be some awkward moments when I'm rapidly trying to fix or switch between windows, so hopefully there'll be a few of them and not too many. All right, so let's get to the topic of our presentation, which is patch attestation with Patatt. Patatt is the tool I wrote, and before we talk about the actual tool, let's go and look at what the state of patch attestation is without it. So, RFC 2822 attestation for mailed-in patches. What options do we have these days? There's two mechanisms of doing it. There's an end-to-end, which means it's developer to developer, developer to maintainer. You sign the patches on your workstations. The developer who reviews them verifies them on their workstation. Or there's domain level, meaning you don't do anything on your workstation. You submit it to your SMTP server. The SMTP server signs it using the DKIM standard, which we'll talk about in a moment. And then the developer basically does nothing to verify it because all the verification is done by your receiving SMTP server, and if the DKIM signature doesn't match, chances are the mail ended up in spam anyway and you didn't see it. So for end-to-end attestation, there's two mechanisms. There's OpenPGP and then there's SMIME. OpenPGP is about as old as each other. OpenPGP was introduced, I believe, late 80s or early 90s. I don't remember which one it is. But in the ensuing 30 years of life, it didn't really solve the problem of key distribution, because key distribution and bootstrapping trust is really a hard problem, and there is no easy sidestepping of that problem. Like, we can create a certification authority, but then you have to trust certification authorities. Obviously, if you don't want to trust anybody, then you have to worry about key distribution and management on your own, and that is the crux of the problem. Another problem with OpenPGP is that the mail client support is still subpar. There are still many mail clients that do not support OpenPGP, or there are those that do support it, but don't do it on a sort of the mobile application or anything like that. Anyway, if you've ever tried to use OpenPGP with signing messages and verifying messages, you know that it's hard to get it configured right, and it's hard to get the tooling to do the right thing when sending and receiving mail. Now, SMIME is another standard for doing the same thing as OpenPGP signatures, but it really is relegated these days to the corporate world. There used to be public certification authorities that would provide you an SMIME certificate for signing a mail, but there used to be two of them 2 years ago. Now it's just only one that does this, and they do it in a really strange fashion. If you try to get a certificate from them for signing a mail, they will send you the certificate, the public key, and the private key, which is totally not how it's supposed to work. So I don't recommend you use them, because that's kind of really sketchy. Anyway, there are vendor-specific end-to-end mechanisms for signing and receiving and verifying mail, Proton Mail, Tutanota, but they're all within the vendor itself. They don't scale outside, so we're not going to talk about them at all. So domain level verification is DKIM. Let's take a look at that in a moment. So patches on OpenPGP. Can we use current OpenPGP standards for signing and verifying patches? Well, yes, but nobody does it because there are important problems with it. One, it breaks code review. If you use the inline attestation, I think you've seen some of that. There's going to be dash, 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 begin PGP sign message, dash, 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 then the body of the patch, then there is dash, 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 begin signature, and then there is the base 64 encoded signature at the very end of the message. And the problem that it introduces, and not just those headers and footers, but also the fact that if there are any double dashes in the message body itself, it will add a dash space before that so it doesn't get confused where the actual signed content starts and ends. And that, of course, becomes a problem because Git itself uses triple dash as a mechanism for logical separation of commit content. So there can be anything that's above the triple dash goes into commit. Anything that's below the triple dash is just auxiliary information for the developer to review the patch. For example, it can contain history of the patch. It can contain the short log, or any sort of information that the maintainer may find useful, but not preserve in the actual commit. So that, if it's in the inline sign message, there will get turned into dash space dash dash dash, and tooling will probably just choke on that, believe me. So MIME-based attestation is a way to solve this problem-ish. By default, it does not sign subject. It does not, the signatures do not include the header metadata like subject and from and date, and that does go into the Git commit. So this is the information that we really kind of want to be included in the signature. So we are there are ways of doing it with Git. You can copy the subject, and you copy the date, and copy the from into the body of the message, and Git will look at that. But almost no tools do this, and it continues to be a problem. And of course, the mail user agents and archivals and everything that can strip the signatures. I've seen this happen all the time. They don't recognize that the PGP signature is a trusted and valid content. They may quarantine it or do anything like that. So the SMTP relays may cause problems verifying this. Also, it does not attempt to solve key distribution. We're not going to talk about it too much. There's a web key directories that sort of stepped up to try to solve this problem, but it continues to persist. DKIM attestation is created to combat spammers, really. So when gmail.com sends an email to you, it wants the to verify to your receiving client to verify that the mail actually came from gmail.com, just so the spammers don't pretend to be anybody from a large company like Microsoft or Google or Facebook and so forth. So Google and Microsoft and Facebook will add a signature, the DKIM-signature header that will contain information about the message, including the body hash, and it will sign it with a private key. And to get the public key, you have to query DNS to retrieve it at a specific domain record. It's actually pretty good. It covers the header metadata. It says there's an H equals, which lists which headers are included in the signature. It includes the body hash, which is actually the entire body canonicalized, and then that's the hash of the body. And then the actual signature includes all the data that precedes the B equals characters in the header. So they will include the body hash, will include the headers, and then the actual header content will be part of the signature. So it really is pretty cool. It's an open standard. It is widely used. It's easy to implement. So it is. I think we should rely on this to a certain degree. So is DKIM good enough to attest patches? It is, but with a few caveats. You know nothing about the infrastructure doing the signing, right? If it's a small developer, mom and pop shop, you probably don't, their key's probably not on an HSM anywhere. It's probably somewhere in there on the main server that is doing mail processing, accessible to the postfix or whatever mail transfer agent that is doing all of the signatures. So if that server is compromised, then all of the email, is suspicious after that, because you don't know if the key was stolen or anything like that. The DNS zones, when you're looking up the public key, you're doing a DNS query. Of course, DNS zones are still not signed. The vast majority of them isn't. Even if they are signed, the DNSSEC is turned off verification for most of the systems that are trying to perform the verification. So, you hope that nobody's done anything nasty for your DNS lookup, but you can also never be sure about that. Now, the problem is that the relaxed body canonicalization. So if you look at the C equals relaxed, that tells you that the body was canonicalized using the relaxed standard. And the relaxed standard, one of the things that it does, it will collapse all the multiple white space into a single space. Not a problem for patches for languages like C or Perl or anything like that, but for languages with syntactic white space like Python, obviously this is going to be a problem, because a return true with a different indent could return you from a verification function, and that'll be a nasty vulnerability. So we can't really rely on DKIM, at least when it's not using the relaxed standard for canonicalization, to really attest patches, because it doesn't quite do it for us. It's better than nothing. If you look at the tools that I provide before, for example, it will use DKIM verification all the time, regardless if it's simple or relaxed canonicalization, because simply it's better than nothing at all. So I suggest that we adopt DKIM for our purposes. We're going to use the standard almost in its exact form. We're going to twist it slightly. We're going to, instead of canonicalizing the body using the relaxed or simple canonicalization, we're first going to pass it through get mail info. And get mail info, one of the things that it does it will look for things like a from or a subject in the body of the message to substitute its own from and subject. It will look at the same for date. It will parse the metadata of the message and the commit message and the patch and present them separately so we can actually see how Git sees them. So we're going to take this information that Git mail info provides us. Then we're going to canonicalize using it simple. And then we're going to not use the DNS for key distribution, but we are going to use our own keyrings. And I will talk slightly about that in the future. And we're going to use OpenPGP instead of RSA or ED259 directly because it just makes sense for us as a kernel development community, because we already are using OpenPGP quite extensively for a lot of other things. So this is the example with OpenPGP SHA-256. We used OpenPGP for actual signatures. We used SHA-56 for creating the hashes of the body and each of the headers. You'll notice that it looks exactly almost like the DKIM signature. There are minor differences there that, for example, we include the length of the message. I won't mention why. There's reasons for that. You can read the code to figure it out. We say we only include the from and the subject headers. We don't care about any other headers because they don't become part of the Git commit, so we can ignore them. And the B content is the output of GNU-PG specifically that we include in direct form, and that includes the date of the signature. We can't actually use the date header from the email itself, because interestingly, git send email will change the date to the latest. So if we sign it and then pass it through git send email, the date header will stop validating. I have no idea why it works this way. It's really maddening, but there are probably reasons why it's this way. So we're not going to sign the date header, but we do include the date of the signature in the OpenPGP standard itself. So we do check those to make sure nothing untoward is happening. Okay. So skipping to, we're obviously not going to do it by hand. I propose that we do it with a tool I wrote called Patatt. Silly name, serious business. It means potatoes in a lot of languages, and I fully appreciate that. And apparently in Norwegian it means false, which is really strange to me, but it just happens to be that way. Doesn't really matter. You can clone it from gitkernel.org. There's the URL right there. You can clone it from GitHub, if that's your thing. You can be from there. You can just install it from pip with PyPI using pip install Patatt. It's there. It's really only a few hundred lines of code. And of course, we don't do our own crypto. We just rely on GNU-PG and on PyNackle if we support the ED259 key directly. We won't mention those in this presentation because we're trying to keep it short. It is for Python 3.6. It's the oldest Python version still supported. It is intended to be used via you set it up once and then you forget that it's there. It's invoked via send email validate. So if you do use git send email, the idea is that you will you configure Patatt once and enable it via the hook. And after that, all the patches is going to be automatically signed before you don't even have to think about it twice before doing it. And I think everybody should sign their patches, because why not? It's just an extra header. All should sign. I'm going to have a demo session. This is sort of the overlook of how it's going to work. You can install it on your own and test it out, or you can just follow me right here. I'm going to switch to the terminal. There we go. And I already have Patatt pre-installed. It's the latest version as of today, maybe later when you're playing with it. And I already cloned the Linux repository here, and I created a commit that you can we can look there, and it pretends that we just released kernel 6.0.0. That's it. It's not. Don't think too much about this. So let's do git format patch. Patch one stood out. Take a look at this commit. This is what the patch looks like. It's really very short. I just changed the version and patch level to 6.0. Now, how do we make this signed with Patatt? Well, first of all, I already have a PGP key generated. Just for the purposes of this example, it's right there. It's got the signature subkey, ED25519. We can use that directly. So let's say git format patch 1, which is pipe it straight. Wait, before we do this, I'm just going to show you my git config. Just so we have the signing key right there, just what you would use for signing git commits directly. So this is the same. It's user.signing key is specified. If that's specified, then Patatt already knows how to find the key that you want to use for your development work. So we're going to do format patch one standard out, and I'm going to pass it directly to Patatt sign. And if we look at the output here, you will see that we gained 2 developer signature, developer key headers. Developer signature contains the information about the actual attestation. It's got the signature. It's very short because we use the EDT59 key. The developer key is really for the purposes of just information. We don't use the information directly from this header to verify the key, verify the signature, because that would be silly, obviously, because we don't carry, we don't trust the contents directly from the same message we're trying to verify. But if you are interested in how to import this key into your keyring or do any other work about it, this is information that you will need to obtain it, right? So it's got the identity is patatt.example.org. It's an OpenPGP key. The fingerprint is right there. So you theoretically should know how to retrieve that from a key server or how to ask this person for the public key. That might go into it right here. So we can pass this straight to Patatt validate, right? Because it's our own key. We already have the public key for it. It says the pass. If there's anything about the body or the headers that was signed that was different, we would have gotten a bad sig. So obviously we don't want to pass all the format patch to Patatt sign. So let's just enable the hook. And there's a convenient command to do this. Install hook. You'll say that it installed the send email validate hook. If we look at the contents of that, you will see that it's just literally just one command, Patatt sign -- hook, and then just whatever is the hook gets on the as an argument. And after this, so let's say get format patch 1, let's say O to send. See, we created that patch. We will now do get send email. And I say dry run because we don't want to annoy anybody. And I would say to send star, right? And you already here see that Patatt was already invoked. It was signed. And if we control C now, if we look at the message as it exists on disk, you will see that there is a signature header present there. So let's say test localhost, because it doesn't really matter for dry run. What do you want? There we go. And if we look now, if this wasn't a dry run, it would have just gone out. But if we look at to send 01, you'll see that the headers were added, even though they weren't there before. This was done by the hook. So any patch that we now generate with format patch, and then we send with get send email, will automatically get those signatures, and we wouldn't have to really worry about Patatt invoking it manually or doing anything like that. Pretty cool, huh? All right, so you signed, you sent the patches. How is the maintainer supposed to verify this patch that it hasn't been tampered? Well, tools like B4 will do it automatically for you. So let's get Case Cook is a good person who is doing using Patatt for all his signing. So we're going to just demonstrate it right here. So we're going to retrieve his message that he sent a few days ago. And you can see that B4 will do 2 attestation verifications. One, it will verify that DKIM signatures are correct, and we can see that they are correct here. The DKIM signatures passes. But it will tell me that there is no key to verify Case Cook at chromium.org, so I don't have it in my keyring. Now I could ask Case to send me the key and import it into my keyring, right? GPG import. Or there is a way to deal with this other ways. There is a repository that I provide on kernel.org that I track. I call it the kernel.org keyring. And you will have to trust me. Unfortunately, there's no way around it. Like I said, bootstrapping trust is hard. So if you want to trust me, you can just clone that repository and use it with B4. Let me look at git config and say, for keyring, look at this repository that we just cloned. And this is the URL will be in the presentation. And you can see that there's a .keyring. And if we're doing a keyring, OpenPGP, chromium.org, Case Cook, and there is a default key that points to the one that we have on file for Case Cook. So now that we have this keyring SRC there, right, we're going to rerun the same command, B4AM, and you will notice that now B4 says, oh, well, we already have the key in the keyring, not the OpenPGP keyring, not the GNU-PG keyring on disk, but we used the keyring that is in the repository. and that key matches and the signature passes, and we can just say this got signed by Case Cook at chromium.org. And this tells us that after the message was sent by Case, via all the SMTP servers, via after it got stored on lower kernel.org, anything else that's been done to it, we can still verify that it has not been modified between when Case sent it off and when we retrieved it. All right, switching back to slides. Let me go back here. This is what we did. The keyring management is still kind of nascent. I'm not going to go into it too much. I'm just going to mention how it works briefly. There will be a command for B4 that will allow you to simplify management of the keyring. Currently, the only thing it does, it can show you the keys that were used for signing a particular message thread. So test that out by yourself if you want. So B4 will use a global GNU-PG keyring. So if you already have a bunch of keys in your keyring, you don't really need to worry about re-importing them for B4 use. We will always look in the keyring, GNU-PG keyring, if we don't find the key elsewhere. But what I suggest is that we stick pub keys into the Git repositories themselves, right? It's not as crazy as it sounds, right? It is a bit of a circular. How do you use the Git repository to verify the Git repository itself? But distributed trust is hard, and this kind of allows us to sidestep the problem. Git repositories are distributed. They're also auditable. You can, for kernel.org, we have the audit trail for all the Git commits. So if there's something bad happens, we can look at the audit trail and figure out who added which key where at which point. The Git commits themselves can be signed and verified. So for example, if there's a maintainer maintaining with a bunch of sub-maintainers or a bunch of contributors that they work with, they can verify their own signature on the Git commits. It'll be one person that kind of acts like as an introducer to all of the other people who are working with that sub-maintainer. This is a hard problem, keyring management and key management, and it's complicated, so I don't want to bog everybody down too much. So I just wanted to point out that if you do have a key in your GNU-PG keyring, you don't really have to do anything else. It will be automatically used. It will be automatically verified if B4 finds the patches signed with that key. Now, sub-maintainers can keep their own keyrings in a separate ref in a repository. For example, if you're a sub-maintainer of a specific driver and you work with 10 contributors who send you patches for the drivers all the time, you can just create your own ref, and there's information for Patatt or B4. You can look into it how it's done, and you can create your own refs like refs meta keyring, and you can just keep their keys there for B4 to use. This is a way to sort of centralize your keyring management. So if you have copies of the repository in other places, it's easy for you to not have to re-import the keys in a bunch of other places. You can use the kernel.org's keyring like I've just demonstrated with my example. Or you could use a fall-through combination of all of the above. B4 will look into any keyring SRC that you specified before it looks in your GNU-PG keyring. So you can play around with it. I recommend that you do this. This is kind of I think a cool idea that allows us to simplify public key management for contributors and for sub-maintainers. So whose keys should be added to the project keyring? It doesn't really make sense for one-off contributors, obviously. So if somebody sent you a patch that you've never worked with this person before, you should always assume the code is malicious, and you should be reviewing with extra zeal, right? But maintainers don't really scale. So if there's somebody that you work with on an ongoing basis, day in, day out, right? You want to be able to sort of have a quick way to verify that the patches that they sent actually did come from this particular person, that they haven't been tampered with and root anywhere. So the keyring management as proposed by Patatt and B4 allows you to add this as an extra sort of protection around your workflow. Doesn't say you should stop being vigilant, constant vigilance as always, but just keep this as an option, especially if you work with a whole bunch of different contributors and you want to make sure that the patches you receive are coming straight from them. Thank you. Questions or comments, send them to tools@linuxkernel.org. Patches are welcome. If you use Patatt and you find that it doesn't do something that you need or before or anything like that, if you do sign the patches, I will get warm and fuzzies, so I will feel very good about that. So please feel free to do that. And that really is all there is to say about it. So thank you very much for being part of this talk. I believe there is questions and answers you can ask me in the chat. I actually have no idea how it works. I hope that somebody introduced this topic, and please ask away, or you can find me on the mailing list or hanging around. Thank you very much. Have a good day.